Okay, well, welcome back to our class on algorithms and data structures. This lecture, we're going to be getting into inheritance and lists. And so this will be a good follow-on to the last lecture where we talked about the Java implementation of inheritance and polymorphism. So chapter 17 introduced us to the ADT sorted list, which maintains its entries in a sorted order. As with many other ADTs, you can implement the sorted list by using either an array or a chain of linked nodes. The advantage of such implementations is their time efficiency. However, they may require you to repeat a portion of the implementation of the ADT list, since the ADT sorted list and list have several operations in common. So we're going to be talking about implementation of a sorted list, designing a base class and efficient implementation of a sorted list. And so that's what we'll go through as we're getting through this material. For using inheritance to implement a sorted list, recall the implementation of the class sorted list that we developed in chapter 17, beginning with segments 1720. Sorted list has an instance of another class LList, and in this case as a data field. Thus, sorted list and LList has a relationship. Several of sorted list methods, namely remove, by position, that is, get entry, contains, clear, get length is empty, and toArray behave like LList methods. If sorted list inherited these methods from LList, we would not have to implement them again as we did in chapter 17. Thus, we could revise a sorted list as follows, as we're showing here. So sorted list inherited methods from LList. There's a pitfall that we want to be careful of, is the implementation contains a pitfall that is a direct result of using inheritance. Although sorted list conveniently inherits methods such as is empty from LList, it also inherits two methods that a client can use to destroy the order of a sorted list. And so these two methods appear in list interface. And so we have to be dealing with those. So what are some possible ways to avoid the pitfall? What can we do to, here are three possibilities. Use sorted list interface in the client's declaration of the sorted list. For example, if a new client contains sorted list interface string slist equals new sorted list, it can use slist to invoke only methods declared within sorted list interface. Notice that the list operation add and replace do not appear in sorted list interface, although using sorted list interface is the way, in this way, can be a good programming practice. That is all it is. A client need only ignore this practice and define the data type of list as sorted list to have all operations of the ADT list available to it. We have already seen how a client can sabotage the sorted list in this case. Implement the list add and replace methods within the class sorted list and give them empty bodies. However, a client that calls either method would be unaware that the method did not do anything. Implement the list add and replace methods within the class sorted list and have them throw an exception when invoked. Note, add also overrides the version that LList implements. If the client invokes this method and an exception occurs, the approach is a common practice and it is one we prefer. So let's design a base case. Let's examine the class LList that we developed in chapter 12 as a linked implementation of the ADT list. Recall that the class places each of the list entries into its own node. These nodes are linked so that the first entry's node references the node of the second entry and so on. A data field first node of the class references the first node, and another data field number of entries counts the number of entries in the list. like most classes, LS has data fields that are private. The client cannot access these fields directly by name. The class designer must decide whether to provide public methods that give the client indirect access to the data field. In that case of LList, the public method getLength enables the client to get the length of the list. The client, however, cannot directly change the list's length. Only other member methods such as add and remove can alter the length. In addition, LList denies the client access to the field first node by not providing public accessor or mutator methods for the field. This design is appropriate as first node is the implementation details that should be hidden from the client. So the excerpt of the class LS given here in the chart that we're showing shows aspects of the class that are relevant to the discussion. Each node is represented by the private class node, which is defined within LList and hidden from the client. The method getNodeAdd facilitates the implementation of other member methods by returning a reference to the node at a given position. We do not want the client to have access to this node since it is part of the underlying representation of the list, so we make the method private. So this is the first part of the this listing, and here is the second part. Now we're getting into the representation in UML. So far, nothing should be new. Now imagine that we want LS to serve as a base class for another class that you are developing. You saw in the previous section of this chapter that the subclass LS, just like a client of LS, cannot access by name anything declared as private within LS. That is, a subclass cannot access the data field first node, the method getNodeAdd, or the class node, as we're showing in this figure. If we want to extend the capability of LS and do so efficiently, the subclass will need access to these aspects of the class, in other words, to the underlying data structure. To enable a subclass to access the data fields by name without giving this access to the client, we could declare first node and number of entries as protected. It is more typical, however, to keep them private and to provide protected methods for only the access we desire. The subclass will need to access the head reference for first node, so we provide a protected get method to do this. Since getLength is public, the subclass can get the value of number of entries. A subclass likely will need to change first node and number of entries, so we could provide protected methods that do so. But while we want an efficient subclass, we also want to keep our data structures intact. So we will not allow a subclass to change these data fields directly. Instead, we can provide protected methods that modify our chain of nodes in a way that can satisfy both of our desires. For example, protected methods can add or remove nodes, updating the chain's length in the process. To prevent a subclass from overriding these protected methods, we declare them as final. No mutators will be available to directly change either the field number of entries or a node's length. Thus, a subclass can alter the chain efficiently, but we are assured that the nodes will be linked correctly and the chain's length will be accurate. So as a result of these discussions, we make some changes to LList. We define a protected method getFirstNode, enabling the subclass to access the header reference first node. We define protected methods to add and remove nodes, changing first node and number of entries as necessary, ensuring that these methods cannot be overridden by making them final is essential to preserving the integrity of the underlying data structure and hence the list. The implementation of these methods use a technique presented in chapter 12. For example, add first node has the following definition, assuming that the node is not null and the interclass node has set and get methods. So the public method of LList and its subclasses can call the previous methods and thereby reduce the chance of error. So for example, we can revise LS methods remove, and we're showing that here on the chart. Next, we make get node at protected and final instead of private. The client still cannot use the method, but the implementation of the class and any subclass can. They cannot, however, change the method by overriding it. We also make the class node protected and final instead of private. Note node will remain hidden from the client, but will be available to any subclass of LList. We could make node data field data and next protected instead of private, but just as we did for LList, we instead make them private and provide protected accessor methods. We also provide a protected set method for a node's data. To ensure the integrity of our chain, we do not allow a subclass to alter the link portion of a node. And so we make that set method private. Thus, the node has the following four methods that we're showing in this chart. Finally, we make node's first constructor protected, but we leave its second constructor private since it sets a node link portion. Making these changes to the class LS results in a new class, which we will name LList revised. In figure 18.2, which we're showing here, illustrates a class and the access that a derived class has to it. We can now extend link chain base and use what remains of LList revised to form the class link chain list as shown in the listing 18.3 and illustrated in figure 18.3. And so we're showing the figure here. We can simplify the previous class LList revised by organizing the portions of it that deal with a chain of linked nodes into an abstract base class. Listing 18.2, which we're listing here, outlines such a class. Link chain base. Note that the class is abstract by virtue of the keyword abstract. Therefore, a client cannot create instances of this class, even though all of the class methods are implemented. Link class list provides list methods without concern for the details of the underlying chain of linked nodes. The base class link chain base can be useful in other contexts as well. You can use it to define an efficient implementation of the ADT sort list, as will be is also discussed in the text. So let's talk about the method add. So the method add in our new class is quite similar to the one in segment 1710 for the class link sort list. However, the details of the previous edition now are hidden within the protected method add first node and add after node of linked chain base. Thus, our revised method appears as follows. And so you can see that here. What about the private node get node before? We still need to implement the private method get node before. The implementation is like the one given in segment 1711, but it uses get first node instead of first node. Okay, that's it for this chapter. Thank you very much.